We ended the previous video by just introducing the idea of Bayesian inference. This idea that it was a combination of a prior belief, what did I think about the parameters before I had any new evidence, pi of theta. What would the likelihood of my new evidence be if I knew theta, f of x given theta? And what do I now think? What distributional belief do I put on what I think about theta given the data set or the set of observations x? So we had this idea that it was the posterior distribution, what I thought after the experiment, was proportional to the prior times the likelihood. So returning to this video footage of me flipping a coin again, what we have is we have this problem of describing the range of values that I believe for theta, which is the probability, the propensity of this coin to land heads when flipped. Let's say, quite reasonably, we think the coin is fair. I give most credibility to 50% or values close to that. I'm not ruling out other values, but I will put much less credence, much less belief that it's a 99% heads coin or a 1% heads coin. I'm going to start initially just with a normal distribution centered on 0.5, where I've set sigma squared to be some known constant as the variance. Now, in fact, this is not a very good prior, because whilst it describes my general belief that the coin's about 50-50, technically speaking, the range of a normal variable is minus infinity to infinity. So this distribution is actually putting some credence on negative probabilities or probabilities above 1. Now, in reality, if I chose sigma squared sensibly, the amount of credibility it's putting on there could be vanishingly small, but technically it's there. So this is not a great model. Work out Bayes' theorem, then I can put in my prior belief, f of theta. I can put in my likelihood, f of x given theta, if I've got a data set, and I should be able to get out then up to this proportion, this constant of proportionality. I should be able to get the posterior, f of theta given my data set. Let's say my observations, I think I coded 0 for tails, 1 for heads. So if I got 0, 1, 1, 0, 0, i.e. tails, heads, heads, tails, tails, then the likelihood of that, the likelihood of getting the first observation as a 0 would be 1 minus theta. The likelihood of the second observation being a 1 is theta. The likelihood of the third observation being a 1 is theta, and so on. So the fact that I got a total of 3 tails and 2 heads will give me a likelihood of that set of observations given a theta of 1 minus theta cubed times theta squared. So the numerator should be easy to work out because I can write down the density function of a normal centered on a half with variance sigma squared. But when I write down the prior times the likelihood, that's just multiplying 1 minus theta cubed times theta squared times this normal density. But integrating that out for the denominator, it's not impossible in this case, but it's messy. It's not nice. But the great advantage of Bayesian methods going hand in hand with MCMC is that the hardest part of the calculation, the annoying bit of the normalizing constant, doesn't matter. And in fact, even more than that, a lot of the other parts of it don't matter as well, because this 1 over 2 pi sigma squared will appear in the posterior likelihood of my proposed point. It'll appear in the posterior likelihood of my current point. So in fact, if I were doing this with MCMC, I can just put a line through a lot of the terms that appear top and bottom and simplify them. So even though I haven't yet defined in a nice, tidy, closed form what the posterior distribution is, I could still sample from it with MCMC quite easily just by drawing from some distribution, calculating an acceptance probability based on this ratio here, and then either accepting or rejecting those proposed moves. And so what we want to see from a Bayesian framework is this idea that it's a blend of what did I think before the evidence, how has the evidence changed my mind. So obviously I want to see the evidence pulling what I believe towards it. How much evidence it takes to pull, well, that's where we have to sort of do the modelling well, and we have to be honest about why did I think the prior belief was what it was. If I take a coin flip example, if I have flipped this same coin 1,000,000 times before and got exactly 500,000 heads, I should be very, very sure it's 50-50. So if I flip the coin twice more and get 2 heads, my 2 bits of new information probably shouldn't influence my prior belief very much in changing it to get the posterior belief, because the weight of new evidence is nothing compared to the weight of credibility I put into the prior. But then there's the other extreme. I pick a coin out of my pocket. I've never seen this coin before. I guess it's a half, but I've no real reason to believe that. So I say, I think it's about a half. But to be honest, I'm happy to be convinced otherwise with a relatively small amount of evidence. Now, for this example, with the coin flip, maybe the advantages of MCMC, they're there, but they're not huge. But the point is, as models become more and more complicated, they become more and more important, or the advantages get greater. So let's say I'm drawing from a normal distribution, but I don't know the mean, and I don't know the variance. Now, that's actually how the world works. We often have to deal with, when we're doing measurements, we're not exact about these things, and we want to know what our uncertainties in the measurements are. I like this image. It's written by a former colleague of mine who's at the University of Technology, Sydney, who's since retired and sadly since died. A great physicist called Les Kirkup. But I also like the image of what goes wrong if your measurements are wrong. So it's a nice image of Sydney, and also a nice wry joke. But let's say here, for this example, I think that the mean is about 10, and I've got some uncertainty on that, with a variance of 0.5, and the sigma squared, again, technically this sigma squared puts some credence on negative variances, but very, very, very little. But I put these in just to illustrate how complicated the model would get. Although the model I defined on the previous slide draws from a normal distribution, I don't know the mean, but my credibility on it is described by normal, and I don't know the variance, but my credibility on its value is described by normal. Sounds simple. When I write the model out, I have this product on the top, which is absolutely awful, and then I have to integrate out over all of those uncertainties in the bottom. So yes, I realize a lot of square root of 2 pi's can cancel, but that is not a calculation which I want to be doing anytime soon. even that simple model gets very ugly very quickly. So even for this example, I've only got two parameters in there describing my uncertainty about mu and sigma squared. This becomes very messy very quickly, and that is why MCMC can be used to fit these models or draw realizations from models where I can define the pieces of it, but putting it all together can become horrible very quickly.